First lab we're going to do is lab 31. Everybody bought their lab book, right? And I can't find my corrections for lab 31. I can't find my book, so we need to open it up and make some corrections in the lab. So diode characteristics. Of course, we're not going to go over the summary theory. We're going to get into the last of this. So we're going to use a 1N914, which is a small signal value. We're not going to use this for rectification. We're just going to look to see and where it breaks over. We'll break this thing over as a class because I think I told y'all. In fact, I'll have to go get some more power supplies. Is this guy here breaks over around 90 volts. I think it's rated at 60, but it actually breaks over around 90 volts. So we'll do that as a class. What we do at this point, so table 31.31, we're not going to measure, we're going to color code those things, right? We're going to use the color coded value. I mean, it's no sense in this class to measure resistors. We do it in DC, and we do it in intro because you're trying to prove laws, right? You're trying to prove that V is equal to I times R. So, every resistor has a tolerance. So what we're trying to do in intro is to make your calculated values closely match your measured values. And it usually falls pretty good because you actually measure the size of these resistors. After we get past that, we understand that our calculated values and our measured values are not going to be the same, right? You understand? But they're going to be what? They're going to be close. I do want you to measure the forward and reverse resistance of the diode. Not on the diode scale, the forward and reverse resistance. So you might have, you got a manual ranging meter, you might have to move that up. And what are we expecting between forward and reverse bias if we measure resistance? We're not using the diode scale, we're measuring. They call it the diode scale, but technically it's a p-n junction scale. We can use that to check any device that has a p-n junction. So we'll use it to check transistors. We'll use it to check, you can use it to check SCRs, even though you got to do something a little different. We'll have to show you that when we get there. So what should we expect forward and reverse? Well, no, believe it or not, most meters will measure it. What we're looking for is a really high ratio between forward and reverse. So forward might measure because your meter's trying to put out only 1 milliamp. It's not stepping up, it's not doing what it would do on the diode scale. You might measure 2-3K forward bias and you might measure 100 meg reverse bias, right? You understand that on the diode scale. Now this is where we run into problems. If I can remember how to do this. Nope, that wasn't it. Oh. Nope. So what we have is we have a, what's this a symbol for right here? So what's this a symbol for? We have variable DC voltage source, right? So on our trainers, you're going to use the variable DC voltage source. And we have a plus and we have a minus variable DC voltage source. I got my, of course I can't get my math. Up until now, I think y'all mostly use the fixed voltage sources. So the problem we have is most DC voltage sources will not go down to 0. And you can see over here, we're going to measure the forward bias voltage across the resistor. So we're going to come over here, we're going to measure the voltage source across the resistor. And we're going to start off with what? 450 millivolts, right? That makes sense. So the diode should be almost turned off. And then we're going to measure the voltage drop across this resistor. And then we're going to compute the current. Everybody know the formula for current? I is equal to what? L-bar. I gotta figure out how to. So this is a common thing that we do in electronics. Instead of using an ammeter, if we've got a series resistor, we don't need an ammeter, right? You understand? Because we can do what? We can measure the voltage across the resistor, and then we can use that to calculate the current. So this is one thing we'll do a lot in here. So the problem is that we're going to have 450 millivolts across here. We're going to have very little current flow through there. And so the problem we have is that the best we can do on these guys is around 2 volts, which is already going to put us down here, right? You understand? So what do y'all think we need to do? I need a way I can adjust that. Not any resistor. A what? We don't even know capacitors in here. Well, no, then we'd be changing it all the time because its resistance would change. So I need something I can adjust the voltage. So, huh? Yeah. What'd you say? Yeah. So what we'll do is we'll modify the circuit a little bit. So we'll come over here, and this will be oh, dang it. Let me turn off the power supply. And we're going to have to do that several times in this lab, guys. I mean, in this book, because they're depending on power supplies and signal generators and stuff that we can adjust down to 0. One of the labs, it says we want like 10 millivolts out of your function generator. I've never seen a function generator that you can adjust it down to what? 10 millivolts. So it's no big deal. Well, let's do one. We'll just use a pot. Still recording. So we're going to come up here. We're going to change our circuit around. We're going to put our variable DC plus DC source. Right? Everybody okay? Reference this to common or ground. I think it's grounded. I hadn't took a meter and decided if that's really a ground or if it's a. We're going to put our pot right here. Then we'll come over here and put our 330 ohm right here. So you're still going to use the 330 to calculate your current. You're going to measure the crosshair. You're going to come over here and you're going to do what now? Here's your diode. So now we should be able to adjust our VF. So we'll come over here with our meter, start off with. We'll adjust it to get to, we'll adjust our pot until we get, don't adjust the power supply, right? So set the power supply at about what? Plus 5 volts. Then after that, we're using the pot as our power supply. Everybody understand that? And now you can take your meter, you can put it over here, set it at 0.45 volts, and then you'll do what? Then you'll come over here and measure across your resistor. Then you'll use that to calculate what? Current. Everybody okay? That makes sense. Any question? It'll be interesting to see what it did. Now what we're going to do, this is what we're going to do as a class. So what you're going to do is somewhere down the line is you're going to develop what we call the VI characteristic curve. We looked at that before, right? So the VI characteristic curve, y'all are going to be working on this side right here. So this is IF. I don't know why I'm zooming. Huh? Yeah, thank you. Thank you. So this is I forward. Do it again. Let me just I'll just stay away from it. So this is IF, and this down here is VF. Okay? And then what we're going to do is we're going to come over here and we're going to plot this curve. Make sense? Of course, we're not going to see this because we're going to start out right around here, which is going to be the 450 millivolt. We're going to see very little current flow through it because it still hasn't fully turned on, right? Understand? And then we're going to keep going up till we get about 0.75 volts, which should be up here somewhere, 750 volts. And then we're going to have line, we're going to have other dots that we come up here and do that. So once you get all these measurements, you should be able to draw that curve. That makes sense? That's one of the things you're going to do in this lab. You actually see that curve. And you should see it slant because this would be third approximation. You're going to actually see the resistance of the diode come into play. Everybody okay? Another thing that you're going to do is you're going to measure, so what is R? What's the form for R? V over I. But what we're going to do is we're going to do an AC on it. So we're going to use what we call delta V over delta I. Now delta means a change in electronics. It means a change in voltage over a change in current. So what you're going to do is you're going to choose two locations, here and here, right? And this would give us a change in current, right, over a change in voltage. So that basically will give you the AC resistance of the diode. That makes sense? Everybody okay there? Any question?
Could it be anywhere on that curve?
I think it's going to tell you the points if I remember right. And you're not worried about the slope, even though it's a slope, because it's fairly linear once we get past 0.7 of a volt. So they'll probably do it up here where it's actually fully turned on, not where it's trying to turn on, where it's fully turned on. So we want it to be above the knee, or whichever way you want to call it. Then we're going to do this as a class. We're going to come over here, and we're going to come over here and do this. And we're going to break the thing over. Now, how are we going to get by with that? Well, what we're going to do is we're going to come up here and use like a 10 mega ohm resistor. So when it does break over, there's not going to be enough current flow through it to do what? Burn it up, right? Understand that? And then we'll come up here and reverse bias this. I could have drawn it the other way. Okay. So what we'll do is we'll start off here. We'll be measuring the voltage drop across that thing. As soon as we reverse bias it, though, we're going to see a little bit of what? Leakage current. And the leakage current is going to steadily increase. But it's going to increase until all of a sudden it increases real fast. As soon as it increases real fast, it means we met the breakover. We exceeded the breakover voltage for the diode, right? And of course, this is going to come out here. It's not going to be that. Now the problem is, if you look at the chart, this guy here has a breakover voltage of around 60 volts. Now what voltages do they give us? So we'll never break this diode over unless we make a what? We change these. So usually what we'll do is we'll do 30. I don't come up here and cause it to zoom in again. So we're going to mark this off and we'll do 30. And then we'll do 60. And then we'll do breakover. Which is probably going to be around 90 volts, but we might have to go. It might break over a little before that or a little less than that. That's just usually where it breaks over. We should be able to see that because I'll be turning the knob and the current will be going up slightly because it's going to be, we're looking at leakage current, right? You understand that? But when it breaks over, it's going to start moving real fast, even though I'm turning my power supply knob, but very, very little bit. Very little bit. Okay? And then again, when you do your VI characteristic curve, you're also going to do the break, oops. So right here, this is your VI characteristic curve. So this is IF, right? This is the IR. Okay? And then this right here would be VF. So this is IF. This down here is IR. Everybody okay? Now they do give you the voltages. We'll have to figure out the scale on this side depending on the maximum current that we get. And once we figure out the maximum current that we get, then we'll set up the scale over here. Everybody okay? Makes sense? Yes, no? Huh?
How do you know where IF and IR is?
But we're going to do IR. We're going to do IR right here. So we're not going to break the circuit, but we got a 1 mega ohm resistor. So to get our current, we're going to measure the voltage drop across this resistor right here, and then we'll calculate the current. Okay. This is going to be IR, right? You understand? These right here are going to be IFs right here. In this chart right here. So these are all forward current. Okay. So we'll go all the way up to 0.75 across our diode. So you're going to have to make two measurements, right? You understand that? But they're all voltage measurements. So what we're going to do is we're going to measure the voltage drop across this resistor, and then we'll use that to do what? To compute the current, right? Like I tell people a lot of times, if I've got a series resistor somewhere, I don't measure current. Because what do you have to do to measure current? What's that? How do you measure current? How does an ammeter work? You have to break the circuit and put it in series. So we could do that. We could take the output of our pod and we could put an ammeter in there all the time, but there's really no big deal, right? You understand that? And you understand you don't have to move your meter lead around. This is what's so neat about this. Sometimes the polarity might chip, but I don't even think the polarity will chip right here. But what you can do, it will. So what you can do is your meter is a meter common. It has nothing to do with ground. So you'll get the wrong polarity, but just ignore the polarity. So what I would do is I would come over here and I'd put my meter common right there. And then I would come over here and I would take my red lead and I would put my red lead right there. Now I'm measuring VR, right? You understand? And then I just move my red lead right there, and now I'm measuring VL. Your VF measurements are going to be negative, but they're not negative. It's just because of the way we put our common on our meter. So here you don't even have to take your meter leads up. If you put your black lead right where I showed you, and then now you have to move to one other side of the resistor and the other side of the diode and record your measurements. But don't record negative, right? Why do we get a negative when we go down to here? Because we're referencing our meter up in the circuit, right? You understand that? So with 1 meter, you can make both those measurements. You can hook up 2 meters if you want to, because that's going to put a lot of garbage up in your circuit. So we'll do this a lot, understanding that it's not going to hurt our meter if we. So that black lead on your meter has nothing to do with the circuit ground or circuit current. It's only if you connect it to circuit. You can put that meter anywhere in the circuit you want to, right? You understand? So back in DC, we have like two resistors, and people would come over here and they'd measure across that one and move their meter, measure across that one. But if you put your common right there, then all you have to do is just go there and then do what? Go there and you're through. You wouldn't even have to move your meter leads. It's just that one of them is going to measure the opposite polarity than what's actually there. We can't do this with a scope probe. So these scope probes, guys, are reference. That right there is reference to earth ground, right there. So you can't probe this sucker anywhere you want to, right? Now an isolated circuit that is not grounded, if it's grounded, by George, you better hook this to the ground, right? You understand? If it's not grounded, you can hook this one probe in there and then you establish a ground, which can be anywhere, right? You understand? But that other meter, the other probe, you have to put it at the same location you put this at. So a good way to check, if you take your meter probe and click it in there and if you see a signal, then that means those suckers are referenced to what? Ground. If you get garbage, it usually means it's not referenced to ground. But meters, we can put that black lead on our meter any way we want to. So we okay? Yes? Okay. So let's look at the data sheet for the let's look at the data sheet for the one in 914. Hopefully y'all got good eyes because that's a little old tiny diode. And sometimes they color code it. So what would 914 be in a color code? That color code, guys, we use that place we use it all over. So what would 914 be color coded? Huh? What would 914 be? What would the numbers 914 be color coded? If they decide to use a color code instead of trying to write this on the side. So y'all don't know y'all's color code. This is also up on the data on the. What's that? Yeah, right there in yellow. So some of the 914s, because the 914 is such a small diode, that what they'll do is they roll it around there. If I was to come up here and so you got to roll this thing to see it. So it's a little old tiny thing, and it's in a glass pack, so it's glass. But they'll put like 1 in, and then they'll put like 9, 1, and then they'll put 4. And so what you have to do is do what? You have to roll it to actually see the part numbers. Because it's a little tiny pack. But sometimes they do the color code. They'll put it on the cathode end, and then they'll put a 3 color code, right? And what was it? A white, brown, yeah. Some of y'all might get the color code on there. We use color code a lot, besides just for resistors. We use the color code on capacitors. There's a lot of capacitors have color code. We use the same color code on inductors. But once you learn that color code, then sometimes these other devices you can put them on. So I didn't see the data sheet there, so let me bring up Blackboard real quick. Lab, and then we have 2 labs we'll do, but before y'all go into the next lab,
Data sheet is in the book.
no, none of the data sheets are in the book. Bring the old data sheets we used to get. You used to get them in a big old book. We got a Motorola book somewhere that's about that big. That has all the components that Motorola put out. We don't get data books anymore. Because why? If you know the part number, you just type in the part number in your search bar. So these data sheets. And what are we really interested in? What's the main things that we're looking for in the data sheet for our diodes? Breakover and current. Yeah, that's good. Nope, wrong class. Okay. Miss Bush started today. But she's been teaching for us for a long time, part-time. She's a full-time instructor, huh? She's full-time. She was working for Revere Controls. No, I'm sorry, she has automation. Wesley or Thomas Hickenbotham works at Revere. Huh? Oh, really? So let's see. This is a signal diode, so it's got very low capacitance. So, here's our breakover voltage. What is it? It says 100 volts, so we might have to go above that. Oh, that's the maximum reverse breakover voltage. Down here, it says around what? Around 70, somewhere between 75 and 100 volts is where it's going to break over. The VF could be anywhere from 620 millivolts all the way up to here. So you could basically set up the AC curve from the data sheet, the AC resistance.
What do we say in test conditions? Is that saying that I should get like 5 microamps and then it's just some that's what I'm looking for?
What do you mean?
I simply say test conditions.
Yeah, it just gives you several test conditions for the data. And all these, by the way, this is pretty standard. All these are at a fixed temperature. So these things were tested at 25 degrees centigrade. So they're saying, okay, it's 25 degrees centigrade, then we should expect these minimum currents. It don't mean you can't have more, but it means you'll never have what? Less. Well, all we know is at 5 milliamps, this guy here is either going to be somewhere between what? 620 and 720. That's all we know. And then they have the reverse leakage current. And then so at 150 degrees centigrade, we shouldn't expect over 50 microamps. So what we'll do is we'll reverse bias it. We'll get it to break over somewhere between 75 and 100 volts. And then what we're going to do is we're going to hit it with a soldering iron, right? Which gets it above 150 volts, and we should see the current just take off. All right, you understand? And then we'll chill it down with some freeze spray. You should see the current drop way down. So the leakage current is predominantly controlled by temperature. So that's why when they do this, normally they give it, so if they don't specify, it's at what? 25 degrees centigrade, but they did get you up to, yeah, so they did get you up to here. So at 75 volts, this guy's going to start breaking over. So here we're going from what? 25 nanoamps, and we're going to be up to 5 microamps. But we're going to measure across that 1 mega ohm resistor, right? You understand? We're going to calculate the current. We should see where it starts to break over. So we'll use 3 power supplies, at least. And we'll hook them up series. So the power supplies on the trainer are like this. So we have 2 power supplies. We have 2 independent power supplies. And this, they say it's ground, but we're not going to use ground anyway. And then here's those little terminals that you have access to. This is the minus terminal, minus V, and this over here would be the what? Plus V. Now, if I take batteries and hook them what we call series 80, what does that mean? Yeah, they have each other. Well, these are already in series 80. So if I don't use my common, if I don't use the ground, then those are series 80. And then I can take the output of this one and run it into another power supply, and I can come up here and do this, right? So I'm not going to hook the common. We're not going to use that. This guy right here gives us around 17 volts. This guy here gives us around 17 volts. So across of them, I can get about 30 volts, right? You understand that? So right now, it's 30 at 60 volts. So if we use 4 of them, I could get over 120 volts. If it works for batteries, it'll work for any DC power supply. People don't think you can do that. It's just I can't use what? I don't use the common. I'll just string them out. And then they're already hooked in series 80. inside the tram.
You said my second result, but I say, these problems, I'll be making another power supply.
Yeah, so this will be, if this is our positive lead, so this will be the one that I'll come up and connect. So this will be my 1 mega ohm resistor. And then my diode is going to be pointed in this direction right here. Right? And then I'm going to take this over here and hook it into my last power supply. We're going to hook it over. All right? Y'all understand that? And then, of course, what we'll do is we'll measure the voltage drop across here. We'll use 2 meters. And then we'll have another meter hooked across there. That way we won't have to move them while we're doing that. And then I'll start adjusting this. Right, we'll end up with, these guys put out around 2 volts. We use 4 power supplies. They'll start off with 8 volts, which is still well below that. And I'll just start turning them up. And then when I get up on the 3rd one, the 4th one, I'm going to go real slow because that's where it's going to do. We should see it break over up there. But even though it breaks over, guys, you know, we're limiting our current with a what? With a 1 mega ohm resistor. So if that 1 mega ohm resistor was in there and I broke that sucker, wasn't in there, and I broke it over, that diode would be gone just like that. But here we're going to break it over for that big resistor. And that's why we have problems with our power supplies is your diodes are unprotected. They don't have a big resistor in series with them. We're hooking them suckers up directly to the what? To the transformer. And all we're dealing with is the R of the transformer, and the R of the transformer has nothing, right? You understand that? So that means if we take one of these diodes in a power supply and we don't have enough VF on the rating, as soon as we turn it on the first time, it's going to bop all of them, right? And that's a peak inverse rating. So it has nothing to do with RMS. So you got to know that peak voltage that it breaks over, right? We're not dealing with RMS or average or anything like that. So you're going to have to do that. Normally we try to double that. Just to be on the safe side, also to help if there's any surges, which are hard to get through. One thing good about transformers are just big inductors. So big inductors, they get their opposition, inductors get their opposition, we call it X of L, is equal to 2 pi FL. So these big old lightning strikes, these guys here generate they're at a real high frequency. I mean, they're way up there. They're real going and going. And a transformer will try to block these strikes, right? You understand that? Some of them can get through, but it's usually an arc through. It's not transformer helps suppress those big voltage spikes that tries to get in. Inductors don't like change. But that's what a big spike would do. So that's why we rate our meters the further we get from the power lines, because the further you get away from that, the more the circuits and stuff are going to suppress that, right? So this is what we'll do, and like we'll say, we'll break it over as a class, because I don't want y'all dealing with it. In this class, we don't want to deal with any high voltage. Let's save that for motor controls. But here, we don't require y'all to wear the PPE, right? Even though I should be wearing some. I'm the instructor, I can break the roof, right? But y'all would have to put on your safety glasses, you'd have to have gloves on and all kinds of stuff, anything above 50 volts. Are we okay? So that's okay on that lab? Everybody okay? Know what they're going to do? Who's missing? Harry. Huh? I'll have to learn. I should be able to learn y'all's name. I know most of y'all. I think we're down. I think we're 6. Who was the other one?